Hello team! In this video we're going to talk about parallel computation. So data centers have large amounts of compute resources. They have lots of servers with thousands of cores, terabytes of memory, petabytes of storage, and fast interconnection networks. So how do we use these resources to make applications actually faster? For example, if we have an application that takes 1000 seconds to run in one core, we would like this application to run faster in the cloud if we could rent 100 cores, for example. In this case, we might want the application to finish in about 10 seconds, as we're using 100 cores. So how do we do this? And there are two things that we should consider. One is efficient use of resources, so we want low overhead when using the CPU, the memory, and the storage. And also, we want the programmer to be efficient so that we can develop applications faster. A common, widely applicable approach to achieve parallelism is data parallelism. And data parallelism applies to applications whose data we can partition in small fractions and we can do analysis on each small fraction separately. So the data comes in, we first split the data into n small parts, and then we ship each part to a different compute node. Each compute node will process that data and compute a partial result. And the speed up that we get should be proportional to the number of compute nodes that we use. For example, if we're using 10 compute nodes, we would want the application to become more or less 10 times faster. And then finally, we're going to combine the partial results from the compute nodes and generate a final result. Consider, for example, DNA sequencing. So we're looking for a specific pattern inside a DNA sequence. So what we do is we get a very large DNA sequence, we split it into small parts, we ship each small part to a different compute node. This compute node will search for the pattern that we're looking for and then send a partial result to this combined node. And then at the end, we're going to combine results from all of the compute nodes to see whether we have that pattern or not. Of course, not all applications allow for data parallelism. So some applications allow data parallelism like image processing and DNA sequencing like I just said, and many other applications do allow for data parallelism, but not all of them. And even if an application allows for data parallelism, we still need to make a few design decisions. So what can be parallelized in that application? How should we split the data and what should be the partial result? And finally, how do we combine these partial results into a final result? So these design decisions are related to what we will need to do when using MapReduce. So data parallelism is great and we're going to use it, but it does have some limitations. One of the limitations, like I said, is that some problems do not allow for data parallelism. And for these, we're going to see different approaches. Another problem is that the amount of parallelism we can extract from a problem may be limited. So in the case where we're using n compute nodes, we want performance to be proportional to n. So we want performance to improve as we use more nodes. But this may not be viable. For example, depending on the data we have, making the splits too small may not be viable. In the DNA example, the DNA sequencing example, if we make each fraction of the DNA too small, we might not be able to search for the sequence. Because, for example, if the partition is smaller than the sequence we're looking for, then we can't ever find that sequence, just to give an extreme example. And finally, most of the time may be used in input-output operations. So let's consider an application where most of the time is spent reading data from disk. So we're taking a very long time reading data from disk, and then the compute itself is reasonably fast. So in this case, using data parallelism may actually make the application slower because we're going to take a very long time reading data from disk, and then we're going to spend additional time sending the data over the network, and then we're going to do this compute that is very fast, and then send the data over the network again, and then run the combine step, and then save the result to disk. It might be better to just run everything in one machine in sequential fashion, and it might be faster. More generally, we want most of the CPU time to be spent in the compute step. So we want the data, reading and split to be reasonably fast, and then the compute step should be taking most of the time. And this is where we're going to get speed up. So our computation is going to become n times faster. And then we also want the combined step to be very fast. And another problem with data parallelism is that there are overheads in using this approach. For example, we need to split the data and combine the partial results, and this requires CPU time. And like we just said, we need to transmit the data between servers, and this takes up network bandwidth and time. So data parallelism doesn't come for free.